All right, so it's recording. Yes, it is. Okay, so summarize what we were talking about last time and then move on. So let's have Newton and Einstein in turn describe our two scenarios. One is, here we are in the classroom. Two is, evil aliens come, knock us out, put us in a perfect mock-up of the classroom in their evil alien rocket ship that's accelerating upwards at 9.8 meters per second squared, and we don't know the difference. And so how do we describe those two situations? So, let's start with Newton. So, let's look at our classroom here. Newton will say, our classroom is an inertial frame of reference. If we let go of things, what do? They fall to the floor, right? Free objects accelerate towards the floor at g equals 9.81 meters per second squared. So how do we account for that? Says Newton. Why does everything fall to the floor, says Newton? Because of the force of gravity. Why? Why? There is a force of gravity. mg towards the floor on every object. So free objects fall to the floor because they've got a force of gravity on them. That makes them fall to the floor. That's the lie we've told you your whole life, is that that's what's going on. It's a lie. We've always lied to you because we knew you weren't ready for the truth yet. That's a lie. But that's the standard picture, our everyday picture of what's going on. An object on a scale has weight because the scale does what? What's the scale doing? I step on the scale, I've got weight. Is the scale pushing up on me? Yes. Sure is. And so what's the net force on me right now, says Newton? 0, right, because am I accelerating? No, no net force. So are there any forces on me? Yes, what are those forces? Gravity pointing down and the normal force from the floor, which could be a scale, pointing up. And so force balance, no acceleration because there's no net force. This is Newton's point of view because the scale pushes up with a contact force that balances the force of gravity. That balances that force of gravity. So that's the picture according to Newton. We're in an inertial frame of reference, but everything has this gravitational force on it that causes things to fall to the floor if they're not attached to anything. But otherwise, I can, for example, hold this thing up by counterbalancing the gravitational force on it. That's the convenient lie we tell ourselves. What questions do you have so far? Okay, evil alien spacecraft. our evil alien spacecraft accelerating upwards at those evil aliens have just decided to make it accelerate with the same value as the acceleration due to gravity at Earth's surface. So it's accelerating upwards at 9.8 meters per second squared. Newton is still speaking here. Is it an inertial frame of reference? It is not, right? Because if I let go of something in the evil alien spacecraft, is there any force on it? No, but is it accelerating? Yes, towards the floor. So Newton's law of inertia isn't obeyed. No force, and yet it's accelerating. But it's just an artifact of being in an accelerating frame of reference. So Newton says it's not an inertial frame. It's not an inertial frame. So I don't want to be making everything analogous. Free objects accelerate towards the floor. Free objects accelerate towards floor. At 9.8 meters per second squared. Why? Is it because there's a force of gravity on everything? Says Newton. No, it's because the acceleration of the frame itself is making everything accelerate towards the floor. Why? The floor is accelerating upwards towards them. So relative to the room, if we attach coordinate system to the room, so relative to the room, they fall to the floor. But as seen from the outside, you see the floor accelerating up and smacking into the objects. But inside the room, you see everything falling towards the floor. Make sense so far? Okay, I'm in the evil alien spacecraft. If I step on a scale, do I have weight? I do. Why? The scale needs to give me the acceleration of the rocket ship. So there's an unbalanced force from the scale on me that gives me the same acceleration as the rocket ship. So an object on a scale has weight. An object on a scale has weight because the scale pushes up with a contact force that gives it the acceleration of the rocket. Because the scale pushes up with an unbalanced contact force. In the classroom we say, well, it's balancing gravity. But in the evil alien spacecraft, it's an unbalanced contact force. Pushes up, the scale pushes up with an unbalanced contact force that gives the object the acceleration of the spacecraft. Wait for people to catch up. Any questions? Anything I didn't write clearly enough? Because I'm just all excited writing quickly, and maybe I'll just like make something that makes somebody say, what? Like maybe somebody named Kathleen, it often happens, you know, so. Speaking for other people too. All right, well, questions at this point? So I asked before, you took mechanics, if you talked about fictitious forces, non-inertial frames of reference. I'll ask that again. Did you talk about like centrifugal force and stuff like that? Like what does that mean when you say briefly? Okay, all right. So here's what we can do. It's a non-inertial frame of reference, so Newton's laws don't hold, but we are free to say, I still want to make something that looks like Newton's second law valid. So in the evil alien spacecraft, we could just invent a fictitious gravitational force on everything. We could just say, well, there's a downwards gravitational force on everything. I'll just associate a force mg downwards on everything and use that as my explanation as to why things fall to the floor. That's called an inertial force or a fictitious force. Nothing stopping us from doing that. Centrifugal force is doing the same thing in a rotating frame of reference. You can use Newton's second law to describe everything as long as in the rotating frame you associate a centrifugal force on every object, m omega squared r, where r is its distance from the axis of rotation. And there's also what's called the Coriolis force as well, whose formula I forget. It's like omega cross v something something, m omega cross v or minus m omega something. I'd have to look it up. I'd have to think about it. But in any case, we can do this. We can invent a fictitious gravitational force mg downwards in the evil alien spacecraft frame. To account for our observations. Evil alien spacecraft frame. To account for all our observations. We can just pretend there's gravity in there. Newton would be perfectly fine with us doing that. We could just pretend there's a downwards force on everything, and that would account for all of our observations, that when you let go of things, they fall to the floor. Well, we just say, well, there's a gravitational force in the frame of the rocket on everything. Things weigh something because there's a gravitational force that the floor is counterbalancing. And we know on the back of our heads, we're just making it up, but we can do it. We can just attach a fictitious force to everything, mg, and go from there. Does that make sense? Are you buying what I'm selling? Okay, time to bring Einstein in after I let everybody catch up. So I'm going to change this to Einstein. Because Einstein says that's actually what we're doing in the classroom too. We're inventing a fictitious gravitational force on everything. Just for convenience, but it ain't real. If people caught up, no, I still see people writing. Write super fast, write. Use your mind. Write with it. But it's okay. What am I talking about? Well, okay. Well, here's me trying to write right-handed. Actually, I I suspect I probably overall better with my right hand than most people are with their left hand, because left-handers are forced to use their right hands more than vice versa. Still, you know, there is the thing, like if I want to throw left-handed, I shouldn't actually throw. If I want to throw left-handed, right, kind of to make a natural. If I want to throw right-handed, I'm like, I just cannot do the motion, you know. Yeah, you probably are the same thing. If you try to, you know, like throw left-handed, if you're a right-hander, you're like, you know, I just can't do it. It's weird. Anyway, how do y'all use this hand? It's so weird. It's just the wrong one. A bunch of freaks, said the person who's the exception. But anyway, I don't care. It's all about me. I'm the standard, according to me. You know what? I agree. There you go. I'll go with that. Okay, can I proceed? You got this part?
If you'd like to use your right hand, sure.
No. Right, to slow my. What's that? So you're still writing this part? Ah, okay.
That is
You're doing a throwing demonstration.
Yes.
So like the previous examples you gave, those are for Newton, and then this one's for
Yeah. Now, so this one is still Newton can say this. For this, Newton is saying this for the evil alien spacecraft that we can invent. So I should have erased classroom there. Newton says we can invent a fictitious gravitational force mg downwards in the evil alien spacecraft frame to account for all of our observations. And Einstein is about to say, yeah, that's what we're doing in the classroom on Earth too. Okay. Well, Kathleen's done. None of the rest of you matter. Are you done? Okay. CJ and Kathleen are done. Now we're done. Are you done yet?
You can erase it, that's fine.
That means you're not done yet.
Oh, I matter now.
You matter. That's right. You matter. That's right. Unless, as they say, unless you multiply you by the speed of light squared, in which case you energy.
Understood.
Yes. Uh-huh.
I'd like to say matter.
Yeah, there you go. Uh-huh. Yep.
And I'm done.
And you're done. Well, now we're done. Okay. Okay. So now Einstein comes along and says, yeah, that's actually what we're doing as a follow-up to what we just said. That's actually what we're doing in the classroom on Earth, too. Two, exclamation point. The rest frame of the classroom is not an inertial frame. Is not an inertial frame. Gravity is curvature of space-time. That alters which frames are inertial. Gravity is a curvature of space-time that alters which frames are inertial. Around a spherically symmetric body. Well, if I really want to be careful, a spherically symmetric, non-rotating body and we're going to say Earth is close enough to this for our purposes here. Earth is close enough for us for now. If I'm really careful. The inertial frames are accelerating towards the center. Accelerating towards the center. The inertial frames are accelerating towards the center of that spherically symmetric body. The rest frame of the classroom is not an inertial frame. Gravity is curvature of space-time that alters which frames are inertial. Around a spherically symmetric, non-rotating body, Earth is close enough for us for now. The inertial frames are accelerating towards the center. So relative to inertial frames, the classroom is doing what? What's our classroom doing? Is it stationary with respect to those frames? Is it accelerating? Yeah, it's accelerating. Which direction? Upwards at 9.8 meters per second squared. So relative to inertial frames, the classroom is accelerating upwards at 9.8 meters per second squared. So it is just like the evil alien spacecraft. It is just like the evil alien spacecraft version. Okay, there's a slight difference we'll talk about in a minute because gravity is stronger at the floor than it is on the ceiling, and the evil alien spacecraft, there would truly be like a uniform gravitational field, but we'll get there. It's just like the evil, just like the evil alien spacecraft version. The force of gravity is a fictitious force we invent for convenience. We invent for convenience. And that's the thing to wrap your head around. That's the huge insight here. Oh, look, a convenient die that I can use. I let go of the die. Why did it accelerate towards the table? Because the table is accelerating upwards relative to inertial frames. What did it do in an inertial frame of reference after I let go of it? It was just hovering in that frame if I let go from rest. Now there would be ones where it was moving, but there's a frame, an inertial frame, where it's just hovering there, and the table and the floor and everything else accelerated up to it, just like an evil alien spacecraft, right? And floor's pushing up on me. Why? Because it's accelerating me. It's giving me that upwards 9.8 meters per second squared acceleration relative to inertial frames. So this floor force on me isn't balancing the force of gravity. It's an unbalanced force that's giving me my upwards acceleration. And that's true for you too. The force you feel from your chair and the table, if your elbows are on, etc., it's giving you your upwards acceleration. It's an unbalanced force giving you your upwards acceleration relative to inertial frames. And that is what gravity is about. It's actually by your foot there, sorry. That, thank you, is what gravity is about, according to Einstein's picture. That's the thing to think carefully about, wrap your head around, because what a different point of view that is. But it's not something that stops being true when you leave the classroom. No, it's always true, right? That's what gravity is. Mass, curved space-time, altering which frames are inertial, and we can invent fictitious gravitational forces in non-inertial frames in order to account for our observations, but that's what we're really doing. How come we never explained to this when you were a freshman? Oh my God, right? Because you weren't ready. You weren't ready for this. You weren't ready for the truth when you were a freshman. But now you're ready for the truth of gravity. Okay? Questions, comments, observations? Yes?
I kind of have a question, but it's a big question. It probably spiraled into a tangent that could last an entire lecture or something.
Well, we'll see what happens.
Okay.
We'll see what happens.
All I'm going to say is that gravity is not a force.
Uh-huh.
Okay.
Yep.
Why are scientists so obsessed with, like, uniting gravity with the other actual forces?
Right. Like why do you say if gravity is not a force, then why do we say it's one of the four forces of nature? My answer to that would be because when we say gravity is one of the four forces of nature, we're not using the word force in exactly the Newtonian point of view. When we use gravity as a force in that context, by force we are meaning a way by which objects interact with one another, such as to alter their motion. And so, from that standpoint, gravity certainly alters the motion of other objects. But it's not by putting a force on them per se, it's by altering the structure of space-time such that they will move differently compared to if the object were not there. That would be my answer to that. It's not being used in exactly the Newtonian F equals rate of change of momentum definition of force in that regard. That's my answer. Yep, but it's a good question, right? Because it is something. It's people do ask that. It's like, well, you just told me gravity is not really a force, and then why do you say it's the force of? Why do we say it's one of the four forces of nature? But that's the standpoint. Okay. All right. So let's note that, as I was saying before, there is a bit of a difference between what's happening in this classroom and what happens in the evil alien spacecraft, because if you carefully weighed something at the ceiling and at the floor, well, you would find that they didn't weigh exactly the same thing, because even from the Newtonian point of view, right, GMM over R squared, the further you are away from the center of Earth, the weaker the gravitational force, quote unquote, becomes from the Newtonian point of view. And it's also true in relativity that the further you are from an object, the smaller the effects of gravity become. So in other words, while in the uniformly accelerating spacecraft, the gravitational field inside is perfectly uniform. Everything would accelerate at exactly the same rate towards the floor no matter where it was in the room. So if you could do really careful measurements, you would find that the acceleration towards the floor when I let go of the die at the ceiling is ever so slightly less than its acceleration if I let it go near the floor. The Newtonian point of view, again, would be gravity's weaker up there. Well, Einstein would agree with that. There would be a difference in their acceleration. So in other words, in a non-uniform gravitational field, we can't completely eliminate the effects of gravity over an entire region of space-time. If we were in a compartment and we dropped it, we were saying, well, that eliminates the effects of gravity. Well, in the Earth's vicinity, it almost does, but again, again, switching to Newton's point of view, the force of gravity is different on the floor than the ceiling, and so if I dropped this room from some height, then two objects would actually start to separate because they didn't have exactly the same acceleration towards the center of the Earth. And so if you are able to make careful enough measurements, you could tell the difference between being in the Evo alien spacecraft and being in this room. Because in the Evo alien spacecraft, there wouldn't be those effects of gravity having different strengths at different locations. So in a non-uniform gravitational field, we cannot completely eliminate gravity over an entire region of space-time. And in practice, all gravitational fields are going to end up being at least a little non-uniform. In a non-uniform gravitational field, we cannot completely eliminate gravity over an entire region of space-time. Over an entire region of space-time. So for example, here's Earth down here, and we've got this compartment in free fall, freely falling compartment. And I release two balls, one close to the ceiling, one close to the floor. Release both balls from rest. Which one's falling faster towards center of Earth? The higher one or the lower one? The lower one is, right? So will the two balls get closer together over time or further apart over time? They'll separate, they'll spread apart over time because the one on the bottom is falling a little tiny bit faster than the one on the top. They will get further apart over time. Farther, I'll say farther. They'll get farther apart over time. But the smaller the compartment, the harder and harder that would be to measure. The smaller the compartment, the smaller the rate at which they'd be separating. I'll add, since lower one falls faster. Lower one falls a little faster. Now, if this compartment is 1,000 miles tall, and you drop it 2,000 miles away from Earth's surface, they'll pretty noticeably be diverging from one another. But if the compartment is 1 meter tall and you drop it from some height above Earth's surface, well, then it starts to be very difficult to measure that they're actually separating from one another. But you could if you had sophisticated enough, precise enough instruments. You can also get them to come together as well. Now I've got the Beatles in my head. Please tell me you know come together like the Beatles. Right, okay, oh my God, okay. All right, so if I do this, if I have the two balls horizontally separated from one another, they'll move together. Why? Because they're both moving towards the center of the Earth, right? So, because their acceleration relative to Earth's surface, those vectors would be tilted a little bit with respect to one another, they'll come together. These balls approach each other as the compartment falls. The fundamental manifestation of gravity is these so-called tidal forces, difference in the effects of gravity for objects which are not at the same location. That's fundamentally how gravity manifests itself. Tidal forces we say tidal forces because that's what raises the tides on Earth. The fact that, again, from the Newtonian point of view, the moon pulls harder on the near side of Earth than it does on the far side of Earth, and ditto the sun. That's why tides arise on Earth. So we call those differential forces like that, again, in the Newtonian picture, tidal forces. And we use the same terminology here. Tidal forces are the fundamental manifestation of gravity. Because a completely uniform gravitational field could be eliminated by going into free fall. If there was a gravitational field throughout the entire universe, quote unquote, well, just be in free fall everywhere in the universe and there's no gravity anymore. So it's really tidal forces, non-uniformity, that fundamentally manifest gravity, that are the thing that you cannot completely eliminate just by changing frames of reference. What questions do you have at this point? And I hope you like thinking about stuff like this, because again, this is the genius of somebody like Einstein, is that they can take these relatively simple things and deduce something super profound out of it, right? That's the thing. The more non-uniform the gravitational field, the smaller the region of space-time over which we can eliminate gravity to a specified precision. If you're near the event horizon of a black hole, you need a really small compartment to eliminate the effects of gravity to a given precision. Near Earth's surface, you can get away with a much bigger compartment. The more non-uniform the gravitational field, the smaller the region of space-time. So roughly speaking, that would be like something like the size of your compartment, the volume of your compartment times the time interval over which you allow that little frame of reference to exist and do your measurements in it. The space-time volume would be like the volume of the compartment times how long the duration of your measurements is. The smaller the region of space-time, the smaller the region of space-time, over which gravity can be eliminated to a specified precision. And now we're ready to talk about, in more detail, the principle of equivalence, in particular the strong principle of equivalence, it's called. Doink. So the weak principle of equivalence essentially just says, well, you can eliminate the kinematic effects of gravity by going into a freely falling frame of reference, or duplicate them by going into a uniformly accelerating frame of reference. The strong in strong principle is the assertion that there's no experiment you could do that would let you know which situation you were in. So, two ways to state the strong principle of equivalence. Number one, in a volume of space and duration of time small enough, in other words, a small enough region of space-time, chords down here, that the gravitational field can be considered constant, the downward pull of gravity can be duplicated by an upward acceleration of the observer. No experiment would allow an observer in a closed compartment, such as the one shown 2 slides back, to know which of the two situations she was actually in. So is it 2 slides back? No, it's more than that now because I added stuff. So in other words, this situation right here where, wait, which one am I going here? I forget which one I'm talking about here. Right, no, yeah, we're doing it where we're doing an upward acceleration of the observer, the evil alien spacecraft. So the assertion is, according to the strong principle of equivalence, there's no experiment you could perform inside this compartment that would tell you that you were in this compartment and not the one back on Earth. That's the idea. As long as the region is small enough that you can't notice things like this happening. And that's why we do that region small enough, time duration small enough. So how big is that? It depends on how much precision you make your measurements to. The more precisely you can measure things, the smaller the compartment and the time interval have to be. But in any case, that's the strong principle of equivalence. It says that you cannot tell the difference. There's no experiment you could perform, including particle physics experiments, anything, that would tell you whether you're in a uniformly accelerating compartment or a uniform gravitational field. There's just no difference between them. Questions? It's an interesting expression. Questions? Yeah? Is it just mind-blowing?
No, I'm just like thinking like.
What's that?
No, I just was like thinking like.
Yeah. I mean, this is profound stuff here. It's profound. It's right? There's no way to tell the difference. No experiment you could do that would let you know the difference. From this, we're going to deduce that gravity slows down time and bends light. Seems innocent enough, but then we're going to say, nope, it's inevitable that it has an effect on time, etc. So that's one version of the principle of equivalence. Okay, stop it. The other version is the effects of gravity are eliminated in a, come on, you can do it. Come on, be a good computer. Come on. Yes, the effects of gravity are eliminated in a freely falling frame of reference as long as the volume of space and duration of time are small enough that the gravitational field can be considered constant. No experiment would allow an observer in a closed compartment to tell if they were floating adrift in deep space or freely falling in a gravitational field. Right? So, of course, you got to get rid of the atmosphere to make this work on Earth. Go into a big evacuated room, get into a compartment, let it drop. Okay, don't, but while you're in the dropping compartment, you will blissfully not be able to tell the difference between that and being adrift in space. So evil aliens capture you from your spacecraft that was adrift in space. They take you back to their home world and they play a short duration trick on you because of how evil they are, where they put you in a mock-up of your spacecraft and drop it in an evacuated tower, and while it's falling, you're like, I'm still in my spacecraft, far from any stars and planets, and I'm going to do some experiments now. And none of your experiments would tell you which of those situations you were in. Now, if they're truly evil, they let you actually hit the ground. But, okay, in any case. All right, makes sense? That's the principle of equivalence. The strong principle says no experiment could be done to tell the difference. So now let's get over there. Look at the implications. Okay? So one implication is, if the principle of equivalence is true, and that's for experiment to decide, and experiment has always said, yep, it's true, then gravity bends the paths of light rays. There must be gravitational deflection of light. So you see all those like gravitational lensing and stuff like that. If the principle of equivalence is true, there must be gravitational lensing. Gravity must affect the paths of light rays, of photons. So here, it's a figure from your book. Here's our scenario. We have a compartment with a cable attached to it, hovering above the surface, and we got a laser that's going to fire a photon horizontally, and right at the moment that we fire the photon, the cable snaps. It doesn't have to actually be at that moment, it just helps kind of mentally to picture it that way. So right at the moment we fire the photon, the cable snaps. What do we see? All right. By the principle of equivalence, the effects of gravity are eliminated in the freely falling compartment. So the photon does the same thing it would do deep in outer space in a compartment that was just adrift, afloat amongst the stars. And we know that if you were adrift amongst the stars, that photon would just travel a straight line across the compartment. And so that means that within the freely falling compartment, the photon must travel in a straight line, just as if the compartment were in deep space, far from any stars and planets. But wait, in Earth's frame of reference, if we're looking at this from the outside, at a frame at rest with respect to Earth instead of from inside the compartment, the photon has to be falling along with the compartment, because the photon's going to hit this wall at the same height it was fired from. But if that's going to happen, the photon has to fall with the compartment in order to hit the opposite wall at the same height that it was fired from. So conclusion, the photon must follow a curved path relative to Earth's surface. Ta-da, basically. That's the implication of all this. So if the principle of equivalence is true, gravity must affect the paths of photons. Questions? So if I fire a laser beam across this room, even if I aim it very much horizontally, it'll hit that wall a bit lower than I launched it from that wall over there. Let's say I put a laser beam over there, I fire it across the room, it hits that wall a little bit lower than it was fired from, no matter how perfectly horizontally I've aimed it. Are you going to see that? Are you going to notice that the photon curved, that the laser beam is curved? No, you're not. Why won't you see that? It's over such a small distance, and also, how long does it take the photon to cross the room? Do you remember, the speed of light is about 1 something per something in convenient units. What is that something per something? And it's good old, so the time unit will be the SI second. The distance unit will be the stupid English distance unit of the, not a mile, feet, yeah. The speed of light to a very good approximation is 1 foot per nanosecond. I should say the nanosecond, right? 1 foot per nanosecond is a good approximation to the speed of light. 1 foot per nanosecond. Okay, each of these tiles is a foot wide, And so it's like 30 tiles or so from one end to the other. Oh, I should count it. Let's see. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 5, 26, 27, 28, 29, 30. So yeah, it's like 32 feet from one side to the other. So it's like 30 nanoseconds for light to cross the room. It doesn't have a whole lot of time to fall very far in 30 nanoseconds. Similarly, if you're in a car and there's a hole in the road above you, if you go very slowly, you'll be like right into the hole. But if you go fast enough, you'll jump over it essentially, right? You'll fall a little bit, but if you're going fast enough so that it doesn't take you very long to cross the big pothole, well, your front tire has dipped a little bit by the time it gets to the other side, but not much, and so you just climb right out of it. That's what the photons are doing. They're moving so fast that they don't have time to fall very far. But in a neutron star, for example, the gravity is strong enough that you could see light beams curving if you fired them around the vicinity of a neutron star. Maybe not over the size of this classroom, but it turns out that you can see well over, if you wouldn't know anything because it all looks uniformly bright, but if you could like put a map on the surface of a neutron star, you'd be able to see around to a lot of the back side of it because light from that side would come around and reach your eyes because of the fact that gravity was curving the paths of the photons. It's freaky. I should send you a link. There's this nice demonstration where you put an Earth map on a neutron star and you can see what it would look like. It's like, holy smoking crap. All right, so that's implication number one. After the break, we'll show that that gravity warps time. It makes time slow down. It must. If the principle of equivalence is true, gravity has to affect time. Ooh, as Kayla will discover later while watching the video. Shall we move onwards and upwards? Let's do this. So a couple of illustrations to show this idea from actually what's a very nice website if you look at the URL to follow. It's like from the 90s, and so it kind of looks like it, but still it's quite effective, I think. Get over there. Get over there. Click. There we go. So, illustration of the deflection of light by gravity using a freely falling frame. So we're using the version of the principle of equivalence that says you can eliminate the effects of gravity by going into a free fall frame. And so here's deep in space. No gravity, no acceleration. The photon moves straight horizontally parallel to the floor. Put in gravity, well, within the frame of I guess it's a house that's being dropped here, or maybe it's a rocket, I don't know. In that frame, the dashed pink line shows that relative to the floor, the photon is traveling horizontally, but since the whole thing is falling in a gravitational field, that must mean, as seen from outside, that the photon is following the blue curved path. And because of the principle of equivalence, it must be that that's going to be the effect of gravity if you don't let it fall, that it's going to follow the curved path, greatly exaggerated here, because of the effects of gravity. Makes sense at this point, what this is illustrating here? That's, okay, you buying it there? All right. Now we can also deduce this from the other version of the principle of equivalence, the one that says that you can duplicate the effects of gravity. Instead of eliminating them, let's duplicate them by going into an accelerating frame of reference. And so this shows that version. Now we're going to use an accelerating frame. I guess it's a rocket ship or it's a house with rockets on the bottom. We launch it. right? Accelerating upwards. No gravity, no acceleration. It just moves straight horizontally. Okay, well, if we're far out in space and we're observing from the outside, then the photon must move along a nice straight horizontal line. But if the rocket is accelerating around the photon while the photon's traveling within it, then the floor is accelerating up towards the photon, so that relative to the accelerating rocket, the photon follows the curved trajectory simply because of the acceleration of the rocket. And again, principal equivalence says that being in the accelerating rocket is entirely equivalent to being in a uniform gravitational field. So if the principal equivalence is true, and experiments show that it is, then we expect to see exactly the same thing in a gravitational field as we would see in the accelerating rocket ship. And so in a gravitational field, a photon follows a curved path. So you can deduce that a photon follows a curved path by either eliminating gravity in a free fall frame, which is what we did with the figure from the book, or going into an accelerating rocket and watch what happens, creating gravity, so to speak, by looking at an accelerating rocket. Okay, are you so far so good with this? Because, oh my God, I'll have to have you explain this on an exam. I mean, I'll just have to have you, right, be able to make this kind of argument here because it's so fundamental. Fundamental, yes. Yes?
So either the light is actually being bent or it just appears to be bent, but either way
So it's a matter of, so it depends on your reference frame, is what it comes down to. So if you are in an inertial frame, well, let's put it this way. In an inertial frame, the light will always go straight. But if you're observing in a non-inertial frame, that will cause it to follow a curved path. And either version of this is saying that. In other words, here we're deep in space. Here's an inertial frame of reference. In an inertial frame, it goes straight. Now, make the frame of reference non-inertial. Well, as seen from the outside inertial frame, it still goes straight. Light always goes straight in an inertial frame. But within the accelerating rocket non-inertial frame, that's where the light follows a curved path. And similarly, if we go to the other version of it with the freely falling frame here, okay, is this, so here we're in outer space, this is an inertial frame. Now we're in the vicinity of a planet with gravity. Is this falling house, or rocket, or whatever it is the rest frame of the rocket falling towards Earth, is that an inertial frame? Yeah, because remember, free fall frames are inertial according to Einstein. Free fall frames are inertial, so it's an inertial frame. The falling frame is an inertial frame. Is light moving straight in that inertial frame? It is. It's following that trajectory that's parallel to the floor within that frame. If you're in that falling frame, you see the light move on a horizontal line parallel to the floor. Light moves straight in inertial frames. But in the non-inertial frame of the Earth's surface, for example, that's where you see the light following the curved trajectory. Now, does that mean that light really curves or doesn't curve? It's a matter of which frame you're looking from. It's a matter of which frame you're looking from. But the thing is that if you have like when we talk about gravitational lensing, right, we haven't emphasized this yet. Because of gravity, in general, you cannot find a single inertial frame of reference that will cover all of space-time. You can only find locally inertial frames, ones that cover small regions of space-time. Our falling compartments are what we call locally inertial frames of reference. We can't cover all of space-time with a single inertial frame of reference if gravity is present. And so from that standpoint, that means that as a result of that, everybody's going to see light curving because there's no single frame of reference that's inertial that you would see it going straight in. You can only locally have it go straight in temporary, locally inertial frames of reference is the idea here. So from that standpoint, yeah, light really does curve because of gravity, because there's no single frame that everybody could agree on that would be inertial, is what it comes down to. Questions? Shall we warp time? All right, let's warp time. First to mention this then. According to general relativity, gravity is a curvature of space-time caused by mass, as summarized by the physicist John Wheeler, who actually coined the term black hole. It's due to John Wheeler. Mass tells space-time how to curve, while space-time tells mass how to move. And so in flat regions of space-time, freely moving objects move in straight lines, but, for example, the mass of the sun causes space-time a curve, and so freely moving objects such as planets and comets and photons, for that matter, follow the straightest possible path allowed by the curvature of space-time. We'll say more about so-called geodesics later on, but in general, and so this is you've seen it before, the stretched rubber sheet analogy. It's only an analogy. Space is three-dimensional, and this is a two-dimensional sheet, and it's, the weakness here is that, well, why is the sun, you make like a bowling ball to represent the sun, and you put it on a stretched rubber sheet, and it bends the sheet. Well, I mean, why is it bending the sheet? Because, quote-unquote, Earth is pulling down on it. And that's not what's really happening in real space-time. It's the sun's mass is curving the space-time around it, et cetera, et cetera. So it's only an analogy, but that's the basic analogy that we make. And so this is showing this qualitatively, this idea of gravitational lensing, where we've got star A and star B behind the sun, and if the sun weren't there, then space-time would be flat, and from Earth we would see star A and star B in their true directions, if you will, from the light following straight lines through flat space-time. But because of the curvature of space-time induced by the sun's mass and energy, but mostly mass, then light from star A, which passes closer to the sun, has its path curve more than light from star B, and where we see a star is along the direction that the light comes to us when it finally reaches us. And so we see star A shifted away from the location of the sun. Now in reality, at the sun's surface, the total shift is about 1 arc second. 1/3600th of a degree, so this is greatly exaggerated. But this is what made Einstein actually become famous, is when in 1919 there was an expedition to a total eclipse of the sun, and they'd photograph the region of the sky where the sun would appear eclipsed like 6 months earlier, and then they photographed it during the eclipse, and they made measurements of star positions on the two photographic plates. And there's some controversy as to whether it was just measurement errors, but they claimed at least to see a systematic shift of the stars away from the sun's location by the amount predicted by Einstein, which would only be about 1 arc second at the rim of the sun, so to speak, at the rim of the eclipsed sun. So principle of equivalence imply this, and then we'll talk more about details of the Schwarzschild metric and where all this is going. Questions at this point? So now let's warp time. Okay, no, enough of it. Let's warp time here, okay? So, thought experiment illustrating gravitational redshift. So, I've done it a little bit differently. I snipped apart your book's illustration of this because I find it easier to make this argument using the version of the principle of equivalence where you use an accelerating rocket ship to duplicate the effects of gravity. Your book does it in a falling compartment. I'm going to have it in a compartment with rockets attached to it that is accelerating with the rockets firing. Okay? So, imagine a photon is emitted on the floor and travels to the ceiling in a compartment that is accelerating upwards in the figure. Okay? So you've got this compartment, there's rockets firing, it's accelerating upwards the whole time, and we fire a photon from the floor to the ceiling, okay? So thus, by the time the photon reaches the ceiling, the compartment is moving upwards faster than it was emitted from the floor. That's step one. By the time it reaches the ceiling, the rocket is moving faster upwards than it was when the photon was emitted at the floor, because the rocket's been accelerating the whole time. Does that make sense? Okay. Well, that means that the meter is moving away from the source of the photon faster than it was. Well, basically they were moving at the same speed, right? The floor and the ceiling are moving at the same speed, but the photon is emitted at this point, and the meter's moving up at a certain speed. By the time it gets to the meter on the ceiling, relative to that point where the photon was emitted, and you could have just had a hole in the floor and had the photon go up through that hole in the floor. It doesn't have to be attached to the rocket in any way. By the time the photon reaches the meter in the ceiling, that meter in the ceiling is moving away from the source of where the photon was emitted. What happens when a detector is moving away from the source of the light? Do you see red shift, blue shift, or no shift? You see red shift, right? You see red shift when you are moving away from a source. You see a red shift of that source. So the argument here is that a meter in the ceiling will measure a red shift of the photon's frequency compared to the frequency with which it was emitted from the floor. If the rocket ship had the rockets not firing, if you just did this in space and it was just either at rest or moving at a constant speed, would you see a red shift or blue shift or no shift in that case? If the rocket is not accelerating, then by the time the photon reaches the ceiling, is the ceiling moving any different? Compared, right? It's not if it's not accelerating, right? So do you see red shift, blue shift, or no shift? No shift in that case, right? If you're deep in space in an unaccelerating rocket ship, you don't see a red shift or a blue shift if you fire a photon from the floor to the ceiling. But in the accelerating rocket ship, if I fire a photon from the floor to the ceiling, the meter will see a red shift because of the fact that the ceiling is moving faster by the time the photon reaches it than it was when the photon was emitted. So you're going to see a Doppler redshift as a result of that. Does that make sense? Find what I'm saying? You will see a Doppler redshift. What if it were going the other direction? What if it was accelerating downwards? By the time it hits the ceiling, red shift, blue shift, or no shift? So now it's accelerating downwards. You'll see a blue shift in that case, right? So red shift, blue shift, right? Red shift in one case, blue shift in another. So in other words, if we reverse, now we just have it still moving upwards, right? If I replace the meter, if I put the meter on the floor and the source on the ceiling, and it's still accelerating upwards, the ceiling, sorry, the floor detector, does it see red shift, blue shift, or no shift? So it's moving up faster and faster. The photon is moving down. So the meter on the floor, is it going to see red shift, blue shift, or no shift by the time the photon reaches it? Blue shift in that case. So this is not symmetric, right? This is not symmetric. Photons fired from the floor to the ceiling are red shifted. Photons fired from the ceiling to the floor are blue shifted. It is not symmetric. And that's because the situation isn't symmetric. One end is on the side where it's moving. I want to say this. It's definitely moving up, and so there's an asymmetry between the thing that's on the ceiling and the thing that's on the floor. So you don't expect them to see the same thing, because in one case, the ceiling meter is moving faster and faster away from the source. The floor meter is moving faster and faster towards the source. if the source is on the ceiling. So it's asymmetric. 1 meter sees redshift, 1 meter sees blue shift. So a meter in the ceiling will measure a redshift of the photon's frequency compared to the frequency with which it was emitted from the floor. So there will be in this case, what we're going to deduce is a gravitational redshift. What questions do you have at this point? Yes?
How does that like physically work, like with absorption and like how does that physically like change the like wavelength, I guess, of the light? Like,
So if I see a redshift of this light, does that cause, so first of all, the speed of light is the speed of light. So the meter will still see the light wave moving at the speed of light.
Yeah.
But it has seen a redshift, so the frequency is smaller. Fewer waves pass by it every second, but they're still passing by at the speed of light. So what happened to the wavelength? It expanded. The wavelength will be larger and the frequency will be smaller in the ceiling compared to the wavelength and frequency that were emitted at the floor. So both effects will happen because a redshift is an increase in the wavelength and a decrease in the frequency. And so, you know, imagine that there are two wave crests, and this is, you look from your point of view, okay, and I'm in the rocket ship, okay? I'm in the rocket ship, but you look at everything from your point of view. From your outside point of view, is anything changing regarding the wavelength or frequency of the light wave? No, because you're just looking from the outside, so there's nothing that's going to cause the wavelength or the frequency to change. So here's two wave crests moving by at the speed of light, and you see them keep a constant distance from one another, right? Okay? But now, look what's happening with me. All right? This one reaches me. Ta-da! All right? Now, I am accelerating, so as this one is approaching me, I'm running faster and faster away from it. What does that do to how long it takes to reach me? It increases how long it takes to reach me. And therefore, I will measure a longer interval between reception of those wave crests because of that. But relativity says I still see them both move past me at the speed of light, so the only way I can explain that is that they were further apart by the time when they reached me, in order to account for the fact that it took me longer to receive the two of them passing by me at the speed of light. So I see an increase in the wavelength compared to what you do. Yes?
So if the wavelength is increasing because that's tied to like the energy of the photon, would that mean you would also read a lower energy?
I would read a lower energy of the photon. That's absolutely right. Yes. Photons climbing in a gravitational field lose energy. They lose energy. And yeah, it's true. It's true. An analogy would be, if I throw this up in the air, what happens to its kinetic energy as it rises? It's decreasing, right? So I fire a photon upwards. Can its speed change? Nope. So the only way it's got to lose energy is to increase its wavelength. You can kind of look at it that way. The photon loses energy as it's climbing out of the gravitational field in the only way that it can, by increasing its wavelength as opposed to increasing into changing its speed, if you like. Okay? And I'll just throw in, as the universe expands, what's happening to the wavelengths of the cosmic microwave background photons? They're increasing, so what's happening to their energy? It's decreasing. Where's it going? It is disappearing from the universe. Energy is not conserved by the universe as a whole. It's just disappearing. It's going nowhere. It's just disappearing. It's actually not true that the universe as a whole conserves energy. And that's because the Hamiltonian of the universe is time-dependent, and energy conservation requires a time-independent Hamiltonian. mechanics. All right, so by the equivalence principle, an accelerating compartment is equivalent to a compartment at rest in a gravitational field. So a photon traveling upwards in a gravitational field, i.e. opposite to the direction of the acceleration due to gravity, will experience a gravitational redshift as it climbs. Conversely, a photon traveling downwards in a gravitational field will experience a gravitational blue shift as it descends. So far, harmless enough. I'm just talking about the wavelengths of photons, getting longer, getting shorter, but now the twist. First I'll leave this up and if anybody wants to write it down or whatever, it's in the slides, but can I push the button? Okay, all right. Gravitational redshift implies gravitational time dilation. Time runs slower, deeper in a gravitational field. They're opposite sides of the same coin. You can't have one without the other. So in our illustration here, apparently we have identical twins on the floor and the ceiling of a building, and they're both watching clocks. And now we imagine, okay, drill a hole through the floors, and there's a light source. You launch a photon from the light source. By the time it reaches the ceiling, it is redshifted, illustrated here by it starts out blue and ends up red. Now, in Earth's vicinity, it's not going to be nearly that extreme, but it's just, it's even if it's a small effect, it's still an effect. So let's make the argument. Okay, this is a thought experiment. Einstein was very fond of thought experiments, experiments that we perform in our minds to deduce things. To deduce logical implications of things. Imagine synchronizing a clock next to the light source on the ground floor so that it ticks, the clock ticks, once every time a wave crest is emitted. So they've got an analog clock there, but suppose I had this digital clock, and you've got this light source, and okay, light sources emit, like 10 to the 15th waves per second, so it'd be extremely rapid here. You could also make it like it's a radio wave instead of a visible light wave. In any case, every time a wave crest comes out of the light source, the digital clock adds one tick. So, whoop tick, whoop tick, whoop tick, whoop tick. Got it? Okay? So, now, I think then, okay, here's the digital clock changed from 0 to 1, so now here is the first moment that the clock reads 1, and that light that was emitted right when it switched to 1 is rising up towards the top of the building. At the same time, the wave crest that was emitted at that tick is following with it, so they're both going to get to the top of the building at exactly the same moment. And so that means the person on the top of the building will receive that wave crest and see the clock changed from 0 to 1 at exactly the same moment. And now there's also the wave crest that was emitted and the clock ticking from 1 to 2 at that time. And so up comes the next wave crest, and the clock, the light that first came out of the clock when it switched to 2, so those get to the ceiling at exactly the same moment. So the person on top receives 2 successive wave crests at exactly the same moment she sees the clock looking down changing from 1 to 2. Because when she looks at the clock, she's not seeing as it is now, she's seeing the light that's reaching her at any given moment. So she sees the clock switch from 1 to 2, 1 tick of the clock, and that's the same amount of time that it takes 2 wave crests successively to pass by her. You buying what I'm selling? That's the idea here. 1 wavelength passes by her in the same amount of time that she sees the clock undergo 2 successive ticks. 1 wavelength, 2 successive ticks, it's the same amount of time. The light from the clock for each tick travels at the same speed as the wave crest next to it, so it arrives at the top floor at the same time. Because of gravitational redshift, the frequency that you see of the the photon is lower on the ceiling, on the top floor, than it was on the bottom floor. You've seen it redshifted. That means the frequency's lower. So because of gravitational redshift, the wave crests arrive at a slower rate on the top floor than they were emitted on the ground floor. Do you buy that? You're seeing the wave crests passing by you at a lower frequency than they were on the ground floor, because that's what a redshift is. It's a reduction in the frequency of the light as observed by you. So you see a lower frequency. They're arriving at a lower rate, but that means so are the ticks, because the ticks were traveling side by side with the wave crests. So you see the clock ticking slower, because every time a wave crest passes by you, you see one tick of the clock. So if the wave crests aren't passing by you, if the wave crests are passing by you at a lower rate than they were emitted on the floor, then you also see the ticks happening at a lower rate than they were on the floor. So you see the clock on the ground floor appearing to be ticking slow compared to a person who's next to the clock on the ground floor watching the ticks being emitted. That's the argument here. If there's gravitational redshift, a reduction in the rate that you receive that you have wave crests pass by you, as seen on the ceiling, then there's also a reduction in the rate that you see ticks from the clock reaching your eyes from the ceiling. So the clock appears to be ticking slow to you. That's the argument, and I want you to be able to make this argument on the test. So if you're not clear, you should ask me right now to explain it again, because I don't necessarily see universal happiness here. Are you happy? You're happy.
I'm sort of walking my head around it.
Okay. All right. So then the question is, and I'll show the slide in a moment, then the question is, well, is this just kind of an optical illusion, right? Because we say that it looks like, oh, I should have the camera on me now. I'm saying that it looks like the clock is ticking slower as seen from the ceiling than the person next to the clock would see from their perspective next to it on the floor. Is this just an illusion? Does it only look like it's ticking slower, but it's not really ticking slower? And I'm going to argue that no, this must be real with another thought experiment that you could in principle actually do. All right, so clock's down there. Or no, let's have the clock down there for now. Okay, I have two clocks. They are absolutely identical in their construction. I have synchronized them. And so I'm holding them next to myself, and I see them ticking at exactly the same rate, right? I keep one of them with me. I slowly lower the other one towards the floor. Okay? I do it slowly so that I don't have to worry about special relativity time dilation. If I do this slowly enough, I don't have to worry about time dilation due to motion. Okay? As I lower this clock, what do I see its rate of ticking do as it drops? It gets slower. And the lower it goes, the slower it goes, right? So slower and slower it ticks. So by the time it's on the floor, then it's ticking as slow as I'm going to see it, all right? And then I start to raise it back up again. What happens to the rate I see it ticking? It gets faster, but is it ever ticking as fast as the clock I kept with me? It's not, because it's always deeper down in the gravitational field. It's always ticking slower. I see it ticking slower than the clock I kept with me. So by the time I get it up here again, I saw it ticking slower the whole time, So by the time I get it up here, they're both ticking at the same rate again, but because this one was always ticking slower, what's true about the what's true about the total time elapsed on the clock that took the round trip compared to the one that I took with me? It will have been less. It will have been less. So therefore, this is real, assuming the principle of equivalence is correct, and that's for experiments, and experiments say it's correct, then it must be that if there's gravitational redshift, there's also gravitational time dilation. That there is a real difference between the flow of time, if you will, deeper down in a gravitational field compared to higher up. And so from, again, I just love this, like the switch this pulls is that it's so simple, right? Will you accept that there could be this principle of equivalence where you wouldn't be able to tell the difference between being in an accelerating rocket ship and being in a uniform gravitational field? Yeah, it doesn't seem so bad. You make the argument, right? All that. And then you say, okay, well, that means that there must be gravitational redshift and gravitational blue shift if you fall in a gravitational field. Okay, that's fine. So photon wavelengths change. Cool. Time dilation because of gravity. Gravity affects time, right? So once you bite the hook, you've been snared, the fish has been caught, and you're forced to realize there must be gravitational time dilation, which is a much harder pill to swallow, so to speak. I mean, it's cool as hell, but it follows from the principle of equivalence. And that's every time I think of it, it just blows my mind that that simple concept implies such a profound thing, right? Ooh, ah, okay. Questions? So my next slide makes the argument, just so it's there permanently. Is this slowing down of time by gravity just an optical illusion? No. Imagine being on the top floor with two clocks that you're synchronized. You have synchronized. One you keep with you, and the other you slowly lower to the ground floor. As it descends, you see it ticking slower and slower, and you slowly bring it back up again, so it appears to tick faster and faster, but it is always appearing to tick slower than the clock you kept with you. Conclusion, by the time the traveling clock gets back to you, less time will have elapsed on it than the one you kept with you. That's that argument that we just made. So this is for reals. It's not just an illusion. It's not something about, well, it's just an illusion caused by the finite travel time or anything like that. No, it's for reals. Yes?
So could you do this if you really pull it around and keep going up in a skyscraper? Do you have like a really sensitive clock?
If you had a sensitive enough clock, then yeah, you could do this. I've mentioned this to a lot of you before. We actually do this all the time, it turns out, because the way GPS works is you've got atomic clocks on these GPS satellites, and you've got a receiver, and it gets signals from multiple GPS satellites, and the satellites timestamp the signals. That they say when they're emitting the signals, and at the same time they say where they are. They know where they are relative, right, in the coordinate frame. And then your receiver is able to detect the time differences when it receives the different signals, and it triangulates its position from that, right? And so it's able to figure out, your receiver figures out where it is by triangulating the arrival times of the signals, because it can say, well, okay, this signal was emitted then, I received it now, how far am I from where the thing emitted the signal? And if you have multiple satellites, then you can solve for the one location you could be in where you'd receive those signals at those times from the different satellites. But the satellites are up in orbit at the geostationary orbital distance. I think, are they, or are they? No, no, they're lower than that, sorry. But they're up in orbit. Yeah, anyway, higher up in Earth's gravitational field, which means that they tick, clocks on them tick at different rates because of gravitational time dilation. And then there's also their motion, their orbital motion. So there's kind of a special relativity time dilation too. But really in general relativity, they can both be combined. It's all general relativity, whether it's motion or gravity or whatever. And if we did not account for gravitational time dilation of the clocks on the GPS satellites, GPS wouldn't work. Because how fast does light travel? About 1 blank per blank a blank. About one foot per nanosecond, right? Well, the gravitational time dilation is nanosecond kind of effect. And so if you didn't account for it, you'd be off by nanoseconds, and every nanosecond of error would be a foot, and quickly GPS, you wouldn't be able to locate yourself because of the error that would be induced by not properly accounting for time dilation. So GPS, in order to work, has to account for the effects of gravitational time dilation. When Einstein first produced general relativity, the thinking was, wow, this is amazing, it's fascinating, it changes fundamentally the way we look at gravity, but boy, the effects are so small in a gravitational field as weak as Earth's that we're never really going to have any practical application of this. And now we have GPS, which is worth billions upon billions of dollars to the economy, and it's a practical application of general relativity, which is why I like to use this as an example for students who have said to me things in the past like, yeah, I'm all for supporting scientific research, but I only think we should fund things that are going to have practical benefits. We shouldn't just fund things that are really of theoretical interest only. Well, I have a lot to say about that involves things like don't be like the cows that I saw in Hawaii that have no idea that they're in the middle of the Pacific Ocean and therefore have no greater view of where they are in the grand scheme of things, but we're not cows, and so we should go beyond the way cows view the world. There's that. But at the same time, we are just terrible at predicting what theoretical developments are going to have practical applications. We're just not smart enough to figure out what's going to be useful. When electricity and magnetism were first being understood, they were party tricks. You know, in other words, Queen Victoria is supposed to have said to, I forget if it was, I can't remember who she said it to. I think it was Michael Faraday or something, but anyway, supposed to have asked one of the pioneers of electromagnetic theory, you know, like, but what use is it? This is fun, it's nice, but of what use is it? You know, what practical value is it? It turns out we've got practical applications of electromagnetic theory now, right? Same deal. Turns out we've got a good practical application of general relativity. We just never know when some theoretical development is going to have immense economic value, and so it just doesn't work to say we should only fund things that have practical results coming out of them, because we can't predict what those are going to be. Okay. Questions, comments, observations? Yes?
This is like not really related, but on the GPS, how do they just calculate like the relative difference in the time between two satellites, or they compare it like a single like known source?
So your receiver is getting signals from multiple satellites, yeah, and it knows where they are because it's telling them where they are. And it knows the time differences from the signals that it received from the different satellites. And that's all it needs, ultimately, in order to triangulate its position. It doesn't need an absolute time, it just needs to know how much different the time was that it received the signals from each of them, because then it can deduce then, well, how far away from it must they have all been? And if I'm this far away from these 7 satellites, what's the best solution to where I would be to be that far away from 7 different satellites, for example? I think you need a minimum of 3, but in practice you use more because there's always measurement errors and stuff like that, you know. And so you can triangulate better with more data points, so to speak. Okay, so we'll get started with what we'll continue on Friday, which is putting the math behind all of this. So let's bring now the Schwarzschild metric into things. But first, we have to remember what the metric of special relativity looks like. How many of you had me for Physics 280? How many did not have me for Physics 280? Okay, so those of you who did not have me for Physics 280, I don't know to what extent Dr. Ding would have talked about these things, but I hope to give you enough that it'll be enough for you to deduce everything that we need here. So, first of all, a metric is a distance measure. It tells you the distance between nearby points on a so-called manifold. So we could think of like a two-dimensional plane is mathematically what we call a manifold. We don't have to worry too much about the precise definition of that. But I'm going to write down the metric on a Euclidean plane. Right, so just the classic XY plane, just flat as can be. And that's going to be dl squared is equal to dx squared plus dy squared for Cartesian coordinates. And for now, at least, I'm putting parentheses around everything because later I may switch to this where I would just write like dx squared, but it's going to be understood that that means dx times dx and not the differential of the quantity x squared. So there's an ambiguity there, right? The differential of the quantity x squared would be 2x dx, would be 2x dx. But what I mean is a little distance dx times itself when I say dx squared. So what do I mean here? Well, dl squared is the distance squared between 2 points whose coordinates differ by dx and dy. So in other words, okay, here's x-axis, here's the y-axis, here's 2 points. There's dl, the distance between those 2 points. What's that little distance right there? Is that dx or dy? That's dy, right? That's the change in their y-coordinates. That's how different their y-coordinates are from one another. And that's dx. That's how different their x-coordinates are from one another. So why is dl squared equal to dx squared plus dy squared? It's just the Pythagorean theorem, right? That's just the Pythagorean theorem, right? The hypotenuse squared is the sum of the squares of the two sides. So dl squared is dx squared plus dy squared. That's the Cartesian coordinates metric on the plane. That's the formula that tells you the distance between 2 nearby points on the plane. I could also put it in polar coordinates. dl squared is, what would it be in polar coordinates? So here is, now, here's 2 points. So there's r and theta for the first point. And I could imagine now making a little triangle that becomes more and more precisely correct as I make the coordinate differences smaller and smaller. So now I'm going to want to think in terms of dr and d theta. How much their r and theta coordinates differ from one another. So here's my first point at r theta. Here's my second point at r plus dr theta plus d theta. Those are its coordinates. I make a little right triangle again, and this will be a better and better, more accurate approximation the closer the 2 points are together, which is fine because it's dr and d theta. They're supposed to be little infinitesimal coordinate differences. What is that distance right there? What's that distance right there? In other words, is that the change in the r coordinate, change in the theta coordinate, or something else? What's that right there?
DR.
That's dr. That's the little dr. That's how different they are in their distances from the origin. Right? So this is dr. This arm right here would be r plus dr. And to an awfully good approximation, this will just be dr. It won't be quite right. If I made this way over here, well, then the projection is getting all weird and so forth. But as long as they're very close to one another, it's awfully good approximation to say that little leg right there is dr, the change in their r coordinates. Are you buying that? Does that make sense? You've seen this sort of thing before, most likely, in either vector calc or E&M. We do this sort of thing there. So this little line is dr. What is this right here? Well, I'm going to say here's the angle d theta, the little change in theta between the 2 points. Is that d theta? Is that distance equal to d theta? It is not. What is this distance equal to? Yes? It's rd theta in the limit as they get very close to one another, right? This isn't exact here because really rd theta would be like this, and you'd have a little arc there. Rd theta is really an arc length, the little arc of a circle. But if these 2 points are very close to one another so that r and r plus dr are practically the same length as one another, then this little arc right here is r d theta. This is dr, this is r d theta. In the limit, as dr and d theta go to 0, that becomes more and more accurate to say those two distances are dr and d theta. Here again is dl, the distance between the 2 points. So dl squared is what squared plus what squared? Well, the hypotenuse squared is the sum of the squares of the 2 sides. So what's this side? So we're going to get a dr squared. And what is this side in length? We need it to be a length, not an angle. It's a length. What length is this little side right here? That you're not immediately jumping out with an answer makes me concerned that you're not following this. Yes? That's rd theta. That's rd. This is dr. This is rd theta. Again, as I've drawn it here, these are just approximations.
Isn't that an angle form though?
What's that?
Isn't that still an angle form?
Well, no, because r times d theta is the physical distance between these 2 points, right? Yeah, so r times d theta. You need the r to bring in the distance units there, if you will, right? So it's dr squared plus rd theta squared. This is the metric on the plane in polar coordinates. That's the metric on the plane in polar coordinates. And that's where we'll stop for today. That's where we'll stop for today. Because what we're going to talk about is, now suppose I have something like the surface of a sphere. It turns out that you cannot find Cartesian coordinates that will cover the surface of a sphere. There are no coordinates x and y that you could define everywhere on the surface of a sphere such that the distance between points is always dx squared plus dy squared. There exists no such coordinate system. And that is an expression of the fact that if you have a bowling ball, can you take a single piece of wrapping paper and smoothly wrap the bowling ball? Have you ever tried it? The answer is no. You can't take a single piece of paper and smoothly wrap a bowling ball. It will always crumple up. And that's because when you're warping that piece of paper, if you could smoothly cover the bowling ball with it, then if that was a piece of graph paper with xy coordinates on it, if you could smoothly cover the bowling ball with it, you would have put xy coordinates on the bowling ball such that the distance between points was everywhere dx squared plus dy squared equals the distance squared. You can't do that. There is no Cartesian coordinate system you can use to cover a sphere. But you could take a bunch of little pieces of paper and make a patchwork covering of the sphere. So you can make a bunch of little Cartesian coordinate systems locally on small pieces of the sphere. And so while there's no universal Cartesian coordinate system to cover the sphere, there are local Cartesian coordinates to cover the sphere. And that has a direct analogy in general relativity. In curved space-time, in genuinely curved space-time due to gravity, there's no single inertial coordinate system that you can use to cover the entire space-time, but you can make local inertial coordinate systems that cover small regions of it, and those local inertial coordinate systems are little freely falling frames that are small and only exist for a certain amount of time. And so it's a nice analogy between wrapping a bowling ball with lots of little strips of paper, and you can cover space-time with local local inertial coordinate systems where the metric of special relativity holds, but there's no single coordinate system where the metric of special relativity holds everywhere. On Friday, we'll bring all of this to flower, so to speak. We'll see where all this leads. We'll put the math behind time dilation and all that sort of thing.